Okay. These are, well, they were sent and bought as natural diamond or quartz crystals. Quartz crystals. And I don't think they're naturally this color. But in China, there's probably a little bit of a language barrier there. And they didn't really, because the crystals themselves are quite natural. They're not like lab grown or anything like that, right? So, and they're cool, man. Look at this crystallization. It is outer radioso. Whoa. Psychedelic. So, quartz only has horizontal striations, does not have vertical striations at all, ever. It can't because of the chemical structure of the crystals. Diamonds, on the other hand, form in both the cubic and the hexagonal system. You get six-sided symmetry this way, but if you look at it this way, you get four-sided symmetry. And you'll find little squares and cubes and stuff like that. Because that's what it is. It's a diamond. Quartz does not have anything except horizontal striations. It cannot have these sideways ones and angly ones and stuff like that. So then you do a hardness test, right? You come down here to the bottom somewhere and you find a place where you don't mind a little scratch, and then you scratch it to see, or use it to scratch something, right? And if you've got a nice big fat ruby, go and make a big scratch on it and see what happens. Because that's what happens with diamonds. You can scratch a ruby. Nothing else can scratch a ruby except a diamond. The hardness test is the most definitive and easiest test for determining most of minerals when you're identifying them, but diamonds in particular, because they are so very, 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 very hard. This is 5 orders of magnitude more hard than a sapphire or a ruby. Only diamond and moissanite, right? Silicon carbide, get to be that hard because they started out probably as quartz or maybe calcite, calcium carbonate, right? And they form nice big crystals, but then under pressure, and they are under pressure deep under the ground, they change. And the light metals are driven off, and it leaves just the carbon. And the carbon lines up in little rows because they're all the same size, right? They're not like different size, like in opals. The thing that makes them bright is how homogeneous the spheres are that make up the opal's structure. This, they're all the same size because they're all the same stuff. They're all carbon. And mostly carbon is carbon-13. That's the stable form of carbon. And it mimics the structure of diamond. It's called close packed cubic. There's one thing in the middle and then 6 around it, and then 3 on the top and 3 on the bottom. That's 7 plus 3 and 3 is 6. 7 and 6 is 13. And so the unit cell of a diamond is 13 atoms lined up in what is more or less a pyramid on top and a pyramid on the bottom. And there it is. It's a 3-sided pyramid because it's a tetrahedron. And tetrahedrons are a 4-sided, they have 4 points. Bum, 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 right? Bum, bum, and bum, and bum. There they are. And they cross each other. And they make up most of the silicon dioxide, aluminum oxide, and carbon. These guys line up in that way because they're all homogeneous in size. So they line up in perfect little orderly rows and columns. And then you get perfect cleavage along these lines. If I take a little sharp chisel, I can go bip, and it'll split perfectly right along that plane of cleavage and leave 2 perfectly flat surfaces on the inside. Pretty cool. And you can chop it down like that to a single, it's like a tetrahedron, a double tetrahedron. Got 3 sides on the top and 3 sides on the bottom, and they kind of twist. See what I mean? They kind of twist. And they join together to make a single thing. A single tetrahedron. Very cool. And beautiful. Cool, huh? Now, I think it's way cool.